Welcome my friends. So welcome to my next lecture. So this lecture my plan is to talk about maxima, minima. You see the title, it's maxima, minima, saddle points. I should say that I already discussed about concept of differentiability. And that means the notions of differentiability for functions of several variables. In particular for scalar field, like if I have a functions from Rn to R, then I already introduced the notions of total derivative, directional derivative and partial derivative. So now I would like to see some sort of applications of the, because we know the concept of differentiability. So as an application you will see the notions of maxima, minima and saddle points. I will explain what do I mean by with that. And then there is a maxima minima means what? That means suppose you have a function f, so and suppose that even say think about that functions of single variable, like real valued functions of real variable. Suppose that maximum and minimum of that function exist. So one of the kind of observation or one of the kind of point you should make that, okay, I know that functions has a maximum and minimum, but at what point it attains that maximum. And I think you know that if your set is compact and if your function is continuous, then there is such things happen. But in the case of say scalar field, if I have a functions from Rn to R, can I talk about those kind of things? Because in that case things will be little different. So in that case first I have to ensure that whether the maxima minima exist, and if it in case maxima minima exist for this function, then what are the points I should say that the maxima minima attain. So these kind of concepts will be also available for several variable functions, in particular for scalar field. So that is maxima, minima and saddle points I will introduce. And then there is a method of Lagrange multiplier, that means there is a constraint maxima. So then constraint extremum I should say, that means I have to find extremum for functions or for some things with respect to some condition if I give, that is called constraint extremum problems. And there is a method called Lagrange multiplier that I will introduce, and using that Lagrange multiplier you will be able to solve those kind of problems. And then finally you have exact differential. That's the kind of plan for this lecture. Let me see how far I can go. Okay, so that's what I have written. This is extreme values of scalar valued functions of vector variable. You see extreme values. Extreme means, actually I will explain what do I mean by extreme. Extreme means could be maximum, could be minimum. So together I am calling it as actually extreme values. And then scalar valued functions, scalar field, that means I will always consider my function f from some set A subset of Rn to real valued. So those kind of functions I will analyze, and I want to talk about the notions of maxima, minima, saddle points and method of Lagrange multipliers. So this is actually learning outcome tentatively for this lecture. So what we have, so I am starting with a function f from a subset of Rn to R. Okay. So I will introduce, these are the notions, that means extreme values of scalar field. So what do I mean by that? That means there is a concept called relative or local maximum or relative of local minimum. So that means I will have a functions f say from Rn to R, then I will explain what do I mean by the local maximum and local minimum. And there is a notion of absolute or global maximum or global minimum. That means if I have a functions from Rn to R, so locally there is a notion of maximum and minimum, and there is a concept called globally. Globally means it defines on whole domain. Okay, so that is called globally. And then there is a notion of what is called critical points and critical values. So in other words, what I am trying to say is that, so if suppose a maxima, minima or extremum exist, so then the natural question is what are the points or what are the points in your domain, so that I can say that yes, those maximum and minimum or extremum, they attains that value. So for that I need to introduce the notion of what is called critical points, and there is an associated critical values. Of course, I will talk about the saddle points. What do I mean by with that? It is actually there is no maximum minimum happen in this point. Of course, mathematically I need to explain what do I mean by with that. That will be there in my, as I go, then you will see what is the definition of saddle points. Then there is a condition called necessary conditions for extremum. So that means if I have a scalar field and suppose extremum exist, okay, then it tells you something in terms of like partial derivatives. So there is a necessary conditions that I will explain. And then we will have two concepts, what is called quadratic forms and their classifications, that I will explain, because once I have the notions of extremum and I would like to find the critical points, then you will see I already introduced the notions of, if I have a function from Rn to R, then notions of Hessian I have defined. Okay. So, there is a notion of Hessian matrix. Okay, if my function is nice means suppose a function is differentiable. So, then there is a way, there is a method to find out the critical points. So, there is a Hessian matrix plays a crucial role, and with that one quadratic forms associated will be there, and I will explain what do I mean by that. So, then quadratic forms and classifications will be there, and finally, you have second order derivative test to determine the nature of critical points. That means, if I have a critical points, then I will explain that whether the functions attains its maxima or minima, or local maxima, local minima, or global maxima, global minima. So, that is the tentative plan for this lecture. Okay. So, let me start with that what do I mean by extremum values of scalar fields. Okay. So, what I am doing, I am starting with a function f from E subset of Rn to R, scalar field, it is defined on the set E domain. So, now second kind of line, it says that if f is continuous, I am assuming that suppose my function is continuous, and suppose your set E is closed and bounded, but I already introduced that means if E is closed and bounded in Rn, in other words E is a compact set, okay, then we know that f attains its maximum and minimum value, right. So, that means suppose you have a function f from set E subset of Rn to R, and suppose I assume that my function f is continuous, along with the fact that my set E is compact, then of course maximum and minimum value on E exist. Okay. Then the question is, once it exists, then I can talk about, okay, can I say that there are some points in your set E, so that maximum and minimum value attains. So, that is how I have written. So, how to find the extremum points? Extremum points either maximum or minimum, okay, points at which f attains the maximum value and minimum value. So, in your real variable case, single variable case, you know that if I have functions from f, say closed interval a b to R, and my function is continuous, then you know that it attains its maximum or supremum or infimum, that you know. A similar sort of kind of phenomenon I would like to investigate in the context of scalar field. So, that is why I assume that, okay, start with your domain E is compact, so that maximum minimum exists. Then I would like to find what are the points in that set E, so that it attains those maximum and minimum value or extremum values. Okay. So, now I have written that before finding an answer to the above questions, so I have to define what do I mean by maximum and minima corresponding to the scalar field f. Okay. So, that I need to introduce, and then I will talk about, okay, how to find the given functions f, so how to find what are the possible points there I can investigate, yes, if extremum exists of that functions, these are the possible points one can check for the attainments of those maximum and minimum values. Okay. So, let me see the first definition first. Okay. So, first definition is that it is called relative or maxima, or relative or local minima, or same thing. Yeah. Okay. So, what is that? So, I am starting with a function f from some set E subset of Rn to R, so is a scalar field. Look at the definition very carefully. So, a point x star in the set domain, in the domain E, a point x star, I will say that it is a point of relative or local minimum of f. Now, the term relative or local, that means I want to talk about the minimum locally. Okay. So, locally means somehow it indicates, okay, you have to somehow talk about neighborhood of that point. Okay. So, that actually reflects in the definition. So, it says that if there exists a positive number R such that this should be true, that means f of x star, that means the value of f at x star should be dominated by the value of x for all x in E with this norm, this is mod of x minus x star. In fact, I should say that this is norm of x minus x star, because x and x star is a point in Rn. So, when I am talking about the distance between x and x star, it should be the usual distance or Euclidean distance, and that I actually denote as norm, sometimes mod. It actually automatically means that, okay, I am talking about the distance between x and x star, and that means I am talking about the Euclidean distance in Rn. So, what I am saying is that you have a function f, and I say that a point x star in that set E is a point of relative or local minimum, either local minimum or relative, both are same. Okay. If there exists a neighborhood of your point x star, okay, so that your value of f at that point always less or equal to value of f at x for any x in that neighborhood. So, locally, so what I am trying to say is that locally around the point x star, the value of f at x star is always less or equal to value of f at x in that neighborhood. If these things happen, then I will say that x star is a point of local minima or relative minima, and the value of f at x star is called the relative or local minimum of f. Okay. In such a case, I am saying in such a case the value of x star, value of f at the point x star is called the relative or local minimum of f. So, there are two things. First, I am talking about the points at which I am saying that it is a local minimum of f. That means the value of the functions at any point in that neighborhood should be greater or equal to the value of that point x star, and the value is called the local relative or local minimum of f. Okay. So, the point x star is called the point of relative or local minima, and f of x star is called the value of f at x star is called the relative or local minimum of f. Okay. So, this is local minima. So of course, one point you should notice that I am dealing with a scalar field. So, therefore, this ordering, it makes sense. So, now it is expected if I instead of range is r, instead of r, if I have r2, this is no more makes sense. So, therefore, it is okay to deal with the function or deal with the scalar field. Okay. So, this is called what is called relative or local minima. Of course, parallelly you can define the similar concept for relative or local maxima. So, then again same thing. So, I will suppose I have a function f from e subset of r into r, a point x star in E, I will say that it is a point of relative or local maxima. That means the value of f, if I take any point x in a neighborhood of x star, the value of f at x should be lesser equal to the value of the point at x star. So, that means it should be lesser equal, the local maxima exist at the point x star. So, that is exactly the things. A point x star in E is said to be a point, I am talking about the point x star, is said to be a point of relative and local maxima of f. If there exists a positive r, that means there exists a neighborhood around the point x star such that the value of f at any x, if I take x from this neighborhood of that point x star, the value of f at x is always less or equal to value of f at x star, and it should be true for all x along with this. I think you should write it's a norm also, Euclidean norm. Okay. So, norm of x. So, that means if I take x from E such that norm of x minus x star is less than r, then value of f at x is always less or equal to value of f at x star. Okay. In such a case, the value at that point x star is called the relative or local maximum of f. So, x star is the point of relative or local maxima, and this is f of x star is called the value of that value is called the relative oblique local maxima of f. This is locally. Whenever I am talking about the existence of local maxima or local minima, that means the point, and you just consider if there is a neighborhood such that this maximum and minimum things happen. Now, look at the definition of global. Now, you can easily guess that once I have done the locally, globally means okay, there should not be any neighborhood, it should true in the whole domain, and it is indeed the case. Okay. A point x star in E is said to be a point of absolute. You should remember the term absolute and global minima. So, that means that minimum value exists at the point x star. So, that is exactly the point. A point x star is said to be a point of absolute or global minima of f. That means the value of f at any point x in the domain should be always greater or equal to the value of f at x star. That means I am talking about the minimum at the point x star, and similarly absolute or global maximum, that means value of f at any point x should be less or equal to value of f at x star. So, that is the maximum. So, that means the point x star is said to be a point of absolute or global maxima if this is true for all x in E. So, local means you just always remember this is the kind of course from the term or from the name you can easily distinguish. So, when I will talk about relative or local, that means the point where the maximum minimum exists, it should be the property should happen or property should be satisfied in a neighborhood of that point x star. And whenever I am talking about global or say absolute, that means maximum minimum of course I am talking about, then the corresponding properties should be true for all x in the domain. So, that is called global or absolute maxima or global or absolute minima. So, this is the kind of definitions of extremum points or extremum values, I should say. So, now Yeah, so this is extremum points or extremum values again. So again, so suppose you have a scalar field. So this is another definitions. So the notion of relative or local maximum and minimum I already explained, along with absolute and global maximum minima I explained. Now I come to the extremum points. Extremum means it's actually both local maximum and minimum. That's the meaning of extremum, and maximum and either maximum or minimum. Okay. So this is, I put it as a definition. I am saying that a point x star in is said to be a point of extremum. You see, it is not minimum or maximum. It is a point of extremum of a, if it is either, see, either local or global, anything. If it is either minimum point or maximum point. So, that means all four possibilities are there. So, that means a point x star, I will say that it is a point of extremum. Either it is a point of say local maximum or local minimum, or it is a point of global maximum or global anything. So, local global could be anything, maximum minimum, whatever it is. So, the point x star, I will say that it is a point of extremum of f. Either it is a local minima or local maxima or global minima or global maxima. Okay. The function value f of x star at the extreme point x star is called the extremum value of f. So, the point x star is called the extremum of f, point of extremum. A point x star is called extremum point of f, and value is called the extremum value of f at this or at that extreme point. Okay. So, first point will come and then the value will come, and that point is known as point of extremum of f, and the value is known as extremum value of f. So, that means either could be local, global, maximum, minimum, could be anything. Okay. So, that is the definitions, extremum points and extremum values. Okay, some example I have given. So, this is relative or local maxima. Now, look at this picture actually. So, this is a picture. Suppose you have a functions from say R2 to R, suppose. So, that means if I draw in the 3-dimensional coordinate plane, 3-dimensional, then it will give you some surface. So, if you draw it, so suppose you have some nice functions which will have this kind of pictures. If I draw it, then you see I have written, so relative maximum. So, now this is the full kind of graph or surfaces. So, now locally you can look. Suppose if I look at that locally. So, locally this is the point, if I consider this is the 1. So, that means the point here, the corresponding value will be this. Okay. So, there actually it should be a relative maximum. So, in that neighborhood actually this is the kind of maximum value, and all other values are lesser or equal to. So, that means relative maximum value exists. Now, look at here. So, another, suppose this is a neighborhood. In this neighborhood, this is, look at this value. So, there of course, there should be a point corresponding that value. This value will be this one. So, this is the again relative minimum value. All the values are greater or equal to that one. Similarly, you have relative maximum is there. In that neighborhood, all the values are lesser or equal to this one. So, this is one of the kind of example where you can at least graphically you can see what do I mean by existence of local maximum and local minima. So, yes, so this is actually global. You see now looking at the pictures, you will see, for example, if I draw or if I consider the functions f from R2 to R such that f of x y is equal to minus x square minus y square. So, it is a functions from R2 to R. So, that means if I draw a graph, it should give you a surface in the 3-dimensional plane. Now, what will be the surface? Its surface is like this one. Okay. So, this is the surface that it is clearly given here. Now, look at this value. Now, this is a point, of course, is a point origin 0 0 0 and R2. Okay. So, what is this? You see I have written the functions f has an absolute maximum at point 0 0, because at 0 0 this is the value. Okay. This is the value, and what about the, by looking at the graph of this function, all the values are lies here. So, that means all are less or equal to this. So, therefore, the absolute maximum exists. So, because the any, if I take any point in R2, all the values will be like here and here and here. Okay. So, and this is actually less or equal to this one. So, this is called actually, this is called a global maximum or global extremum, I should say. And on the other hand, if you see this kind of functions, f is a map from R2 to R, or f of x y is equal to x square plus y square, then it will have a absolute minimum at the point 0 0. Again, you just draw a picture, it will be like that. Okay. And if I take this value, okay, this is the value. So, at the point 0 0, and all other values are greater or equal to, because these are the all other points values, always greater or equal to this one. Okay. So, therefore, you can see this is actually absolute minimum or global minimum, I should say. So, that is how pictorially one can look at what do I mean by absolute or global extremum. Okay, so this is relative again, and some pictorially you can look at it, relative or local extremum and saddle point. Okay, I will explain what do I mean by saddle point. Actually the point is called a saddle point, where you cannot have a local minimum as well as local maxima. So that kind of things it's called the saddle point. Okay, just look at the picture, you will see, you can easily identify that this is the point where you have a absolute maxima, because all other the values, so this is the highest peak out of all. So therefore you can talk about this is actually absolute maxima. Okay, or locally you can say that this is locally, actually this is local maxima, or of course absolute, also absolute, it is also absolute by looking at the whole pictures. Okay, so this is also local maxima, I already pointed out, this is another local maxima. Okay, and this is also local minima, you can see this is also local minima. But now this is the point, if I consider this is actually kind of the saddle point. I have written, you see, saddle point means neither a maxima nor a minima, even though surface levels up. So what I mean is that, so if I have a functions draw like this kind of thing, suppose this along with this. So now look at this point here. So this point, whatever neighborhood I can consider, you see, whatever neighborhood, in that neighborhood some values will be bigger than this one, and if I have a value here, it should be less than. So if I have a say small neighborhood, say, so this is my value. Okay, one of the values, if I take this value, then some value I will have here which is smaller than this one. Similarly, some value I will have here which is bigger than. So therefore this point is neither a maximum nor a minimum. So this kind of point I will say the saddle point. Of course, I will give a definitions mathematically what do I mean by the saddle point. Nevertheless, the pictorially you can see, of course it's not fully visible from here, but at least the point where this kind of phenomenon will happen, where you cannot have a maximum and cannot have a minimum near about that point is called a saddle point. And if the local maxima, local minima or global maxima exist, then it clearly indicates from the picture. So pictorially I am actually giving some kind of idea of what do I mean by with local maxima, local minima, or global maxima, global minima, along with the saddle point. Okay, so now as I said, so suppose you have a functions or you have a scalar field, and suppose the maximum minima exist, then the natural question is, can I talk about some points where it attains? So to do that, so the notions of critical points and critical values are there. So first you have to look for critical points, and out of critical points you can check, okay, in those critical points there is a chance of there is a possibility of the function can attain those local maxima, local minima, or global maxima, global minima. So that means first I have to identify what do I mean by critical points. So that means you see, if I have a scalar field and if I suppose ensure you that, okay, yes, maxima, minima, or local maxima, local minima, or global maxima, global minima exist. So now the question is, if I say that what are the points, I can say that, okay, at that point the local maxima, local minima, or global maxima, global minima exist. Now your domain has infinitely many points, right? So now a priori it is very difficult to find out. So what are the points I can talk about it attains those extremum values. However, there is a way. So instead of looking at all the points, you just look at what are the critical points. I'll explain what do you mean by critical points. And once you have those critical points, you just check whether it attains or get the value and just verify from the definition of your functions. Yes, this is the smallest value, this is the largest value in a neighborhood or globally or on whole set. Then you can say that yes, at those points my functions attain those extremum values. So that is why you need to have the concept of critical points. You don't have to go through all the points in your domain, rather you just focus on your critical points and check, yes, these are the points, and you get the values and you can conclude that yes, local minima, local maxima, or global minima, or global maxima. So first I have to give the definitions. So what is my definition? Suppose I have a scalar field, okay, a point x star in E is called a critical point if, okay. So what are the two conditions? Either. So either this or that. Either this means, so I want that a point x star in E is a critical point if all the partial derivative of f first order partial derivatives, okay, then del f del x1. So f is a function from Rn to R, right? So how many partial derivatives we will have? N many partial derivatives, del f del x1, del f del x2 up to del f del xn. If all the first order partial derivative vanishes at the point x star, then I will say that this point is a critical point. This is one of the conditions. Or suppose at least one of the first order partial derivative of f does not exist, then also I will say that my point is a critical point. Okay. So now I hope that the definition of critical point is clear. If I have a scalar field, if I say that a point x star is a critical point, what we have to do, if all the first order partial derivative vanishes at that point, then I will say that this is a critical point, or if one of the partial derivative does not exist. And the function value, that means the value of f at the point x star critical points, is called the critical value. And later you will see that if I want to check the point of extremum, that means local extremum or local minima, local maxima, or global minima, global maxima, it is enough to check on the critical points. Okay, so that you will see later when I will talk about. There is a method actually. You have to. I will go through many examples, then you will see what do I mean by with that. Okay, but you have to first get what are the critical points, and then you just investigate your functional behavior on those critical points to talk about the existence of extremum points. Okay, so one example I have given critical points. One example, you see, first example is that, okay, the point 0, 0 is a critical point of these functions and the critical value is 0. So it's easy, okay, because this is my functions f from R2 to R. So it is a map from R2 to R, okay. So very nice functions, okay, it's a polynomial in x and y. So you just, what is the definition of critical points? So either a point x star in E is a critical point if all the first order partial derivative vanishes at that point, or you have to ensure that, okay, one of the partial derivative at that point does not exist. Now this function is very nice, polynomial in x square, it's differentiable functions. So that means all the first order partial derivative exists. That means you have to just check the point where my first order partial derivative vanishes. So you just calculate, very easy. So what is my first order partial derivative? Del f del x at the point x y. You just take the derivative, keeping y is constant. Think about it as a function of single variable. So what is the derivative? This should be 2x. What is del f del y at the point x y? Again, you keep the x variable fixed. Think about it as a function of single variable y and make the derivative. This should be 2y. So now I want a point where the first order partial derivative at that point vanishes. So that means this should be 0 and this should be 0. And what it will imply? That means we have the only point xy is equal to 0, 0. So origin is the point where my first order partial derivative vanishes. So therefore it is a critical point. And what will be the critical value? Value at that critical point. So therefore value of f at 0, 0, which is 0 by definition. So therefore the point 0, 0 is a critical point because your first order partial derivative vanishes at that point, and the critical value, that means value of f at the critical point, is nothing but 0. It is called the critical value corresponding to this critical point. This is one example. Another example, look, this 0, 0 is also a critical point for this kind of functions. Now again, this sort of functions you already familiar with in my earlier lectures, like this is a very nice function except it has a breaking point. What is my breaking point? Breaking point is again 0, 0, right? So x is non-zero, it gives this one, x is 0, it gives this one. So now look, what I concluded is that the partial derivative of h with respect to x variable does not exist. However, partial derivative of h with respect to y at the point 0, 0, it exists and it works. You can calculate it, and it does not exist. You can just calculate it. Okay, what is this? This is nothing but by definitions limit, say partial, right? So I should say limit x approaches to 0, h of x 0 minus h of 0, 0 by x. Okay, this is the partial derivative of h with respect to x variable at the point 0. So what is this? This is limit x approaches to 0, h of x 0. So that means if I have h of x 0, that means what will happen? Y is 0, y is 0. So that means what will be my point? Here x is non-zero, so that means it should be x sine 1 by x, okay, plus 0 because y is 0. Okay, minus h 0, 0. So h 0, 0 means x is 0, y is 0. So that means this is y. So that means this is 0 divided by x. What is this? This is limit x approaches to 0, x sine 1 by x divided by x. And what is this? Limit x approaches to 0, x get cancelled, you will have sine 1 by x. But what is the limit x approaches to 0 sine 1 by x? Limit does not exist by sequential criteria. So this limit does not exist, and therefore hx, that being partial derivative of h with respect to x variable at the point 0, 0 does not exist. However, partial derivative of h with respect to y variable at 0, 0 it exists because you just use the apply the definition. This should be limit, say y approaches to 0, f of 0 comma y minus f of 0, 0 divided by y. What is this? This is limit y approaches to 0, f of 0 y, that means x is 0 and y. So that means it should be y minus 0 by y, and this should be exactly equal to 1, and that's I have written. So that means what I observed is that, so for these functions, the breaking point is 0, 0. In fact, x is non-zero, there is a huge breaking point. I am putting only conditions at the point x. When x is non-zero and x is 0, that means if I have this one, so x is non-zero, okay, so this is my 0, 0 point. So breaking point is not on the second coordinate y, but however in the first coordinate. So that means if x is equal to 0, y could be non-zero, non-zero, I don't care. So this value is constant y, and if x is non-zero and y could be again 0, non-zero, what will be, then value will be this one. So if I have, I should not say it's a breaking point at 0, 0. Of course 0 is a breaking point, along with there are many points it breaks. However, the function is very nice in a sense, it's a combination of your sine functions and polynomials, right? So, and you can explicitly calculate, as I have done, that means partial derivatives of h with respect to x variable at the point 0, 0 does not exist because of this limit. However, that partial derivative with respect to y variable exists. So, but now what is that in the definitions of critical points, I know even if one of the partial derivative, first order partial derivative does not exist at that point, then that point also a point, critical point. So, in that sense it is actually critical point 0, 0. So, critical point does not imply that always that you have to have the first order partial derivative exists and that vanishes. No. So, two options are there. If all the first order partial derivatives at that point exist and they become 0, then it will be a critical point. Else, if one of the first order partial derivative does not exist, then it is a critical point. Okay. So, first example, all the first order partial derivative exist. Okay. So, therefore, you just check at which point those first order partial derivative vanishes. So, therefore, I just check that 0, 0 is the only point. And the second example, it's like not the existence of the first order partial derivatives at that point, then also it is also a critical point. Okay. There is a common confusion. So, when someone goes for checking, okay, let's check the critical points. So, what they used to do, suppose first order partial derivative exists, so they just compute the first order partial derivatives, then you will have a couple of equations and you solve it, because all the first order partial derivative has to be 0 at that point. Then you will get a couple of equations, and if you solve it, then you will get some point and you say that okay, these are all critical points. Answer is yes, but these are critical points, that perfectly all right, but these are not all. That is very important, because some point where partial derivative, one of the first order partial derivative does not exist, that is also a critical point. So, one has to be careful. So just because of solving partial differential first order partial derivatives, getting some couple of equation and solving it and saying that this is the exhaustive list of critical points, this is not the correct statement. You have to check some points where some of the partial derivative does not exist, you have to include those as well. To talk about your extremum points of extremum some functions. Okay. So, maybe those kind of situation will come to when I will say that okay, investigate the point of extremums or extremum value. Some of the situation will arise where we will have both kind of things will be there, that some points where one of the first order partial does not exist, and that point you have to take into account that to talk about when checking the extremum of your functions f. Okay, now as I said, so there is a definition of saddle point. So, what is saddle point? So, again I said a point is called a saddle point. There is no local maxima or local minima or global, whatever it is. Okay. So, that is I think local or relative, I am talking about relative maxima, relative minima. Okay. So, definitions, a point x star is called the critical point of f. So, I am starting with a critical point. Okay. To talk about saddle points, I am starting with a critical point. So, let x star be a critical point if every neighborhood n x star of the point x star, okay, every neighborhood, whatever neighborhood I can take, every neighborhood x star contains point at which f is strictly greater than f of x star. Okay. So, that means whatever neighborhood I can consider around the point x star, there exists a point such that f is strictly greater than the f is means the value of f at that point is strictly greater than f of x star. Also, it contains a point at which the value is less than f of x star. So, that means suppose I am talking about the critical point x star. Okay. So, suppose this is my point x star, x star. So, whatever neighborhood I can take, any neighborhood. So, there should exist a point say x1 where my value of f at x1 should be strictly greater than f of x star, and there is another point x2, this is my point, such that f of x2 should be less than f of strictly less than f of x star. So, that means I have one point where my functional value is strictly greater than, I have another point where my functional value is strictly less than. That means the point x star is not a local maxima or local minima. That is exactly. So, that means f attains neither relative maxima nor relative minimum at that point x star, and that point x star is called the saddle point. Okay. So, one example I have given. So, this is my functions f of x y is equal to y square minus x square, x y in R2, then I am talking about the point 0 0 is a saddle point. So, that is the picture is there. So, I have kind of this picture is given for these functions. Look at this point. So, this is the point I am talking about. This is a saddle point, because if I look at the picture, of course, it is not, I cannot explain it completely, but you have to feel it by looking at the picture, because it is like here you will have, and along with here this. So, you will have this along with this in that side and that side. Okay. So, as I already explained in my last things is that, so whatever neighborhood I can take, any neighborhood. So, I will have one point where my value increases, I will have another point where my value, I can have the existence of one point where the value of my functions at that point is greater than the value at the point 0 0, and I again get another point existence where my value of that functions or functional value at that point is actually less than the value of this point. So, therefore, neither relative maxima nor relative minima exist, and therefore, this point is called a saddle point. Okay. So, this is I tried to explain in pictorially here. Okay. So, I think I should stop here. So, this is like the notions of critical points. Then I talked about saddle points. So, of course, what are the things I have defined? I have a scalar field. Then I talked about what do I mean by relative or local maxima, relative or local minima, along with absolute or global maxima, absolute and global minima. Okay. Then I said that, okay, I have given couple of examples. Then I said that yes, one of the point is that if I ensure you that yes, suppose local maxima or local minima or global maxima, global minima exist, then what are the points it might attain those points. So, there then I have introduced the notion of critical points and associated critical value, and of course, there is a point called saddle point where you do not have the point attains neither relative maxima nor relative minima at that point, at that critical point. So, these are the kind of definitions I have introduced. In my next lecture, I will talk about, okay, so like if I have a functions, I will explain, give some examples. Look, this is the functions, and find that local maxima, local minima or global maxima, global minima. Then there is a process or there is a method. That means first you have to calculate that what are the critical values, and of course critical values definitions I have already discussed, and then you have to check that if I have finally many critical values, if you will get, it depends on what sort of functions I am going to investigate, and if I have those critical values, then you have to just evaluate your functions and look at the behavior of that functions near about that point. It depends whether I am talking about relative or local maxima minima or local extrema, or whether I have a global extremum. So, it depends. So, those kind of examples will be there, maybe some examples, and there are of course certain necessary conditions from extremum. I will explain, there is a theorem. So, those kind of things I will talk about, and of course, Lagrange multiplier at the end I will talk about along with exact differentials. Okay. So, I think I should stop here. In my next lecture, I will start with again the kind of how to get, of course, I will produce couple of examples, and then I will give some necessary conditions for extremum along with some examples where I will explicitly explain that, okay, this is my functions and these are the points where extremum value either local or global exist. Okay. Thank you.